Okay, so we'll start off with the first lecture.
Okay. All okay? So welcome to week 2. Are you all ready? Okay. So, so last week we talked a lot about the random walk, central limit theorem, law of large numbers, and then we spent, actually in retrospect, we went back to elements of probability theory, and then we covered a lot of stuff on various things, especially the things that pertain to our cause. Now, so in this set of 3 lectures, I'll attempt something slightly different, not really different, in the sense of broad philosophy of what we are doing, but a little different in terms of the actual sorts of models we consider. So we've been considering, just to remind you, let me spend 5 minutes on what we have been discussing so far, models of stochastic dynamics, meaning the time development, that is dynamics, is stochastic, meaning that at every stage you have an option. Stochastic will mean that you have options at every stage, like in the random walk, this which way to step. And options need a choice. Choice is made. The choice you make in one history will be different from the choice you make in another history, and the system evolves. Okay, now, so what we have in the end are outcomes, right? There is an outcome, and associated with an outcome is an event, either way. So as we said, it pays to ask and be very clear about what is the event we are talking about. When we are talking about coin tossing, what is the event we are talking about, or in the random walk language? For instance, I mean, for instance, e.g., reaching site M in n steps of a random walk. This is an event. It could have happened in many ways, we are well aware of that, but this is the event we want. In contradistinction to another event, you might ask, that you fix M and you ask how long does it take to reach there, and that we saw the distribution of times required to reach a particular spot, let us say the origin, was very broad and different, and of course the two are completely different. So it does not matter what the answer is, but be clear on the question. Okay. All right, never mind. So that is just a normal thing that any teacher will tell a bunch of students, be clear. Yes?
So reaching the site M is not an event in itself.
No, so after site, yeah. After n steps.
Yes, after n steps.
Yes, it's not a single event, I agree.
No, but you were talking about the time as well. So then the event is the same, we are looking at a different aspect related to the same event perhaps?
No, perhaps not. No. So in this case, for instance, we are asking n steps have passed, some time has passed. In some time, so let us draw world lines. So in n steps, what could the random walker have done? This is, what do I want? Time, and this is space. So after n steps of time t, the walker may have reached there. We are fixing time. Some other time it may have reached there. Okay, since we have the luxury of colored chalks, it may have reached there. It may have reached there again. You never know. So at a fixed time, you could ask, what is the probability that at that fixed time you are at this site? That is the one this refers to. The other one refers to how long did you take. So for instance, in the same sort of spirit, we could put x versus t and say we want to come back to the origin, let us say. I mean, you could have chosen any other point. So, one history which does come back and then goes on, and I sort of remind you, come back for the first time. That was what we had asked. Another history which comes back is this. So, it comes back at this point. And the third history which comes back perhaps is this. So, it is coming back right here. So, it's the distribution of these points we are asking when we fix the site. Okay? So, it is very different. Here we are taking a distribution along here, and the claim is that this distribution will be a Gaussian. Here we are taking a distribution along there, and the claim is that the distribution will be that power law with 3 by 2. So, be clear. Not only are the questions different, also the answers are different. Perhaps not so surprising, the questions are different. Okay? All right. So, it pays to be very clear. You know, how to be clear? Okay, everybody feels they are clear, but little nagging doubt. Best thing, write an English sentence. Write a sentence in English. What is, I mean, I do it routinely all the time, and I urge students to do it. Sometimes they do it, sometimes they don't. Sometimes they succeed without doing it. But sometimes they don't. You know, so please write sentences. What is the probability of? The moment you write that, you will be forced to think. Please write English. Okay. Now, okay, good. Now, as we said, there were two okay. So let's say you were interested in this PMN, probability of reaching site M after n steps. That is the simpler question to ask. That is the straightforward question to ask. That's the first important question to ask, which was translated into P of x and t. There were two ways we could have gone about finding P of x and t, and we actually talked about both. First way was to actually go back and look at different histories. Count how many histories contribute to the event that you want, weight them, W-I-G-H-T, weight them with the proper weight and sum over them. Okay, so that is one way to find, so I will just write summing over weights of the proper histories. Or in short, summing over, of course, weights is understood over proper histories. That sum would give you a probability, and then you can vary m and so on and look at that. But the other way, okay, and then having P of mn, you could translate to P of x and t and say you have the time dependence. So, this was one way, perfectly fine way, and this is a good way to do it. The other way was to write down an equation of motion for P itself. You know, so, I will just remind you what we wrote is, so the other way is to write an equation for time evolution of P itself. Turned out to be a partial differential equation with x and t. So, we can't fix x and write something for t. You have to write an equation for both x and t, and the equation was, we wrote it dp by dt. We wrote it, I believe we wrote it, I am sure we wrote it. This is the diffusion equation, or rather the diffusion drift equation. C was the drift velocity, d was the diffusion constant. C had units centimeter per second, d had units centimeter squared per second. So, if you divided d by c, we got a length. We talked at length about that length, that was the diffusion length. All that I won't go back into. But I just wanted to tell you that remind you that there were these two ways of doing things. All right, so this is the background. for what we did. Now, I just want to perhaps leave this part of the revision by drawing. Okay. Now, one important thing we did, which will sort of important, a little important in setting the stage here, is that we also considered a random walker where the step lengths are drawn from any probability distribution P of x which had a finite variance. So, recall that. Or step, I should not say lengths, I should say displacements drawn. I am talking about individual steps, small p of x. So, we said small p of x. You remember the context? Anybody remember? What? Nobody? I thought at least one person would remember. Okay, yeah, well, you remember we talked about a random walker takes steps of various lengths. Yeah, so that one, p of x. Okay, that we discussed, but suppose we were to imagine that this is the time axis and this is the step axis, step length delta, and we ask what was the step length here, 2, 3, 4, lots of times, and the step lengths are unpredictable, they are drawn from that probability distribution, but first time maybe it was this big, second time maybe that big, third time maybe this, fourth time maybe this, right. So, the signal of step lengths would have looked like this. It is noisy. It is what you might be tempted to call noise. Not noise of the acoustic sort, but noise, and then jittery, unpredictable things. Yeah, and this of course went on, and I just want to keep this picture on the board. And whereas there is not much you could have said about any one step length, you can't say anything almost other than that it occurs with probability p of x. So, what does it mean that the probability is p of x? It means that if you take a histogram along here between x and x plus dx, and you count how many things fall in this window, that will be px dx. I am just translating back into probability. Yes, sorry? Divide by total, yes, because it is a probability. Correct. You count the number and count the number you have reached up to there and get a normalized probability. That you could do. So, whereas there is not so much you can say other than that you will recover the distribution p of x if you do it long enough. On the other hand, we could say quite a lot about the sums of variables. For instance, we took a reasonably sized bin like this of time, that is some time interval delta t, and you asked what is the distribution of the combined step lengths, meaning this plus this plus this plus this. There we have an answer, and that is a Gaussian. In other words, what I am saying is if you just add up step lengths in some reasonably large interval, you will get a Gaussian. What was that now? Oh, this got caught here. So, this distribution of delta, or I am calling it x here, I keep changing notation. Let us just call this, okay, delta. So, you want to add up the deltas. So, okay, let me go back to x because we are more familiar with adding x's. So, x over some constant, but that constant will be proportional to delta t. Okay, so just keep this in mind, constant times delta t. We'll have some use for this as we go ahead. But these are all results from last week. Now let's go to results from this week. Okay, let us begin. So, what I am going to treat is something called the Landreman equation, all right. And it refers to a very important physical situation typified by a single small but not terribly small particle like a colloid, let us say micron sized, immersed in a beaker of liquid, say water, at some reasonable temperature, say room temperature. And we ask what happens to this particle. Well, so we know for one thing gravity acts on the particle. So, there is a force mg which will act on the particle, all right. So, there is gravity, but okay, in addition as it moves, there is a viscous resistance to the motion coming from the viscosity of friction from the liquid. But that is not all. As people in the early 20th century recognized, I mean, if you blow up the particle and look at it, it is being bombarded from all sides by molecules. At every tiny instant, namely the instant should be smaller than the time taken for two successive molecules to hit, every tiny instant this suffers a small impact. Exercise, work out this time for a micron sized particle. Assume normal density of water, you know Avogadro number, etc., etc. Work out how small this time interval is between successive hits. One molecule is hit for some time, nothing happens, and then another molecule hits. Of course, that time is going to be very, very, very small. And the larger the system, the smaller the time, because more molecules will be hitting it. But for size 1 micron, please make an estimate. You will get a very, very tiny number. All right. So, we will assume, I think with a fair degree of making an approximation which is really very good, that first of all that these bombardments are independent of each other, and that they occur very, very fast, and it sort of resembles this plot. So, it is like noise. Of course, there is a vector character to the noise that is not so material, but there is a noise. But this is a noise in a force, or translated to divide by m, acceleration. Therefore, if we plotted this plot like this, the axis is not displacement, it is velocity. Velocity suffers increments because of acceleration, right? Okay. So, therefore, one writes down an equation of motion for the velocity. du by dt, u is the velocity of the particle at time t, has two terms only, minus beta u. This is the frictional drag. It acts in a direction opposite to the instantaneous motion, all right. And we add a term a of t, which is a random acceleration. That is all. This is the end. This is called the Landreman equation. We are neglecting gravity for the moment. Why are we neglecting gravity? I mean, you can add it in, it is not a big deal. We are neglecting it because the particle is tiny and the dominant forces are these. That is why. When you describe sedimentation or some process like that, it is essential, of course, to consider gravity, and you can easily incorporate it, but in the simplest situation, let us not do that. So, this is Newton's law for the particle subject to random forcing. So, let me just write a little bit here. This is random acceleration, and it is supposed to represent the effect of molecular acceleration. radiation molecular impact. This is a friction term. And if the particle is spherical and is immersed in, has radius a and immersed in a liquid of viscosity eta, what is the value? Oh, everybody knows this, I see. Yeah, so 6 pi eta a would be a good way to approximate this, but of course if the shape is different, that, I mean, proportional to that, but the 6 pi and all will change. As far as I know, not much is known about a general shape. PK, can you follow? Okay. All right. Yeah. Even this calculation of 6 pi eta is not a trivial calculation. It was first done by Stokes. You remember Stokes is the person who was an authority on many things, in the sense that if people came up with new set of mathematics and something they wanted to check, they would write a letter to Stokes, and Stokes would reply. Famous example is Maxwell. See, Maxwell read the papers of, sorry for the digression, but anyway, Maxwell read the papers of Clausius and others, where they talked about molecules and mean free paths. And molecules hit each other and they did this and they did that. But implicit in Clausius's work was the following fact, that he thought, he knew, I mean, everybody understood that when things collide and all, they'll become random. But what is the nature of the randomness? So that Clausius thought, I think Clausius thought, right, that things are all in different directions. They're random in direction, but if you had a distribution of speeds also to start with, after collisions they'll all equalize and become one speed. One speed but random directions, Clausius. Or let us say, let us not say Clausius, let us say earlier work, to make it little earlier than Maxwell, except for one paper. I mean, okay. So Maxwell then thought about the problem and collisions, and he was convinced, and correctly so, that there is a distribution of velocities. So he fairly quickly derived it. And you know, you and I might be quite happy with deriving a new distribution which was not known to anybody, and then saying, okay, this is a new distribution, and you know, writing a paper. Maxwell was not content with that. He worked out the physical consequences. No, please. So he worked out the consequences of having such a distribution, and one of the consequences was that if you have a fairly dilute gas, then the viscosity will be independent of the density. I mean, that follows from the theory. Now, Maxwell could not get himself to believe that. That how can it be? I mean, you know, there's something wrong. So what did he do? He sent his derivation to Stokes. So he said, dear Stokes, can you please check this? So Stokes, of course, checked it. The algebra was okay. He sent it back and said, dear Maxwell, this is okay. Maxwell was in a further problem now, how to understand this. So what did Maxwell do then? He did the experiment. He took dilute gases and he did the experiment, and he found that indeed it is independent of density. Then he believed his distribution. The viscosity, right. And then he believed his answer, and then he wrote it up and sent it. Let this be a salutary lesson for all of us. Only thing Maxwell did not know is that 14 years before him, somebody in Bombay had already derived the distribution. I mean, he didn't write the distribution as a distribution, but he has first of all understood that there is a distribution. He had derived the equipartition of energy and many other things about it. And that was the person I mentioned, John James Waterston. Okay, but it was not known to Maxwell. But anyway, the important thing is Stokes. So coming back to Stokes, 6 pi eta a. Okay. All right. Now, So, here we are with this equation and we want to analyze this. Okay, so the what are the attributes of A? So, we will be guided by this picture on these sort of random steps interpreted now as random accelerations. The average of A, well, so assuming the steps were equally likely back and forth, the average step displacement would have been 0, right, as many up as down. Is this okay? Divyamani, you are looking skeptical. Is it okay? So the mass is the mass with respect to the medium. Okay, so you're right. No, but you know, as we said in the beginning, we are thinking of the magnitudes of forces, and if the gravity effect is very small, we'll throw it out. That is one thing. So we are not including it. We can't include it without much cost. But second, where is the mass in the equation? It is divided out. I mean, we're just not writing it. I mean, if you, this is du by dt is acceleration, you should write m du by dt is something false, but we're dividing by mass, and therefore we're talking about accelerations and not. Okay, so it's just simple division by m, nothing else. Okay, now the thing is, this equation can be solved, and it can be solved immediately by all of you if you just look at it. Yes. Okay, so we are not modeling the actual kinematics of collisions in any detail. Okay, so what are the collisions? So here is the colloidal particle. One molecule comes and hits it. Okay, so you can certainly work out the effect of that hit, and the effect will be to impart a small change of the particle's velocity, assuming it was moving already. Okay, so that we are not going to do in detail because it's just too complicated. Why? Because there are too many molecules. So instead, we adopt a statistical point of view. So there are so many particles and they are hitting that it is reasonable to think that the hits will be from this side and that side and will constitute some sort of random signal like that. It's an assumption, but it's a very good assumption. Moreover, being statistical, we are also in a position to say something about probability distributions, which we will in a minute. Not quite, not exactly, almost, but you see what is the random element, random thing is acting. See, okay, so suppose we wanted to represent a random walk in this language. What would we say? We have a displacement x changing in time, and it can change forward or backward. So we would write this is equal to some noise eta, and we can solve this equation. We are not doing that. We are saying the randomness affects the velocity. So there is a slight difference, important difference. So velocity does a random walk. Yes, at this stage and in the end also it is.
No, because in some they try, what they do is that they try to rationalize this term as saying that it's only small displacement, and then they do a Taylor expansion and retain the first term.
Oh, okay.
But that somehow doesn't seem, I mean, that somehow tells you that we are looking at small deviations about the end. But that doesn't have to be. So I think that
I don't think so. Right. I don't know, I haven't seen it, but I'm certainly assuming it is sort of a analogical friction. And if you read the first Einstein, I mean, not first, I mean the 1905, yeah, I mean this is more or less what he does. So, I mean, I know it is bad to cite authority, but then if it's Einstein, you know, it's almost not authority. Okay, so about Einstein, but we just say that this is reasonable. We just proceed reasonably. You know, in physics, that is a good attitude. Don't try to go back to absolute basics. Be reasonable and go ahead. Don't go back. Once in a while, go back to understand, but biased random walk forward. Okay, right. Okay, A. So average A would be 0. Average step length was 0. However, A of t, suppose we ask for the, how is A correlated with itself? These are all vectors. Let's go back to this. Step length of the step of the random walk, forward here, backward. There was no correlation between one step and the other. That was the whole point of the random walk. So there is no correlation between these except if t equals t prime, which is enforced by t. Then there could be a correlation, and the correlation here of p of x was characterized by, in our way of doing it, some number sigma squared. I mean, that was important. Sigma squared was the variance. So the variance was sigma squared that would have entered this distribution. Here we will not use the sigma squared, we will call it 2q. Okay. By the way, this treatment that I am following is along the lines of Chandrasekhar. You all remember the article that I told you about? Please read it. Please read it. Yes. And you will find that this is, even the notation is similar. Okay, so you will find this there. Now, this is some details about the acceleration, but as a differential equation, can you all solve this? Forget about vector sign. It's a linear equation. If you had just this, could you solve it? It would be what? It's of the form dy by dx equals minus some constant times x. Can somebody solve this quickly? Proportional to e to the minus cx. That we can solve. But then now we have another term which depends on x, but we don't know what it is, f of x. Can we solve this? Yes, we can, through the method of integrating factors. Has everybody heard about integrating factor? I think you all have all heard about it. Some of you may need to revise it, but then please revise it. I am going to not go back and derive the integrating factor, but write the solution. Linear equation with the inhomogeneous term, solution possible. Oh, say y. Oh, sorry, thank you. Cy. Yeah. Everybody gets the right answer. Thank you. Whoever noticed, thanks. Yes. Good. So then we write down the answer. The answer is the following. U, this is it. I mean, we solve the equation, finished. U naught e to the minus beta t plus, okay, let me, in fact, it's this plus something, let me write it as an equation in this one. U minus that is equal to, and here comes that integrating factor, e to the minus beta t integral 0 to t d, okay, dummy variable psi, a of psi e to the beta psi. Solution. Question, can we find the distribution of U? We just discussed somebody who found the distribution of U. That was Maxwell. Does anybody know the answer for the distribution? In other words, I am asking velocity distribution of an ideal gas. Or any gas, I mean by ideal, classical gas. Very good, right, correct. So you all recall that. So somehow at the end of the day, we should get that answer at least at large times. Why do I say large times? Because I have an initial condition. Initial condition is u0. I didn't say what u0 is. u0 is the speed of the particle at time 0, the velocity of the particle at time 0. So it may take some, so if u0 is the velocity of the particle at time 0, after 0 plus 10 to the minus 40 seconds, it will still be about 0. Maybe one molecule has it. It won't, of course 40 is exaggeration, 22, 23, I don't know. Some 2-3 molecules have hit it. It won't change much, it will still be u0. It will take some time for it to become randomized. So at large times you will expect that the answer will become that, but we will find the answer at all times. Is the, what should I say, intention clear? We are trying to find the probability here, I should say, probability distribution of velocities. Where does the probabilistic element come in? It comes in because of this probabilistic hits by molecules, which are AT. Okay, put in a vector here. Once in a while you put in vectors. All right. Okay, in order to do this, we will follow Chandrasekhar's development and we will prove a lemma. And it's a very nice and simple, I mean, it looks very sort of bulky and all, but it's very simple. The lemma says that if you define a quantity r as the integral of psi, okay, how is it defined? Integral d psi. Okay. So what we will do is we will put in some function, some known function of psi, which is not very rapidly varying, by the way. Okay, just to tell you, say, times a of psi. That's all. 0 to t. Question: what is the distribution of r? That is what you will ask, and you will prove that the distribution has a certain form. It is of course going to be Gaussian. The question is, what is the width of the Gaussian? Important to understand what psi is. So it varies, I will use the word gently. Gentle. In this day and age, everybody is used to gentle reminders. Are you or not? I mean, I keep getting gentle. They're actually not gentle. Do it. But this one is really gentle. Gentle in the sense that it does not vary like A does. A varies like crazy. Suppose for the sake of argument, you have to work out what I said, that time scale, but suppose for the sake of argument that time scale is 10 to the minus 24 seconds. On the time scale of 10 to the minus 12 seconds, there are many 10 to the minus 24s which have happened there. So psi may be varying on that scale, for instance, and t may be 1 millisecond. So you are integrating, psi is varying slowly, but in that there are a lot of variations. So coming back to that picture, but let me just draw that picture again. What we might have, see here we were thinking of the same distribution p of x throughout. Now what this is doing is modulating the distribution. So if you draw this, you will first find these things, but after a while you notice that they are growing, for instance. I mean, this is supposed to be the noise, huh? And then maybe it's growing more. Why is it growing? Because of the multiplication by psi. Psi is the amplification factor for the acceleration. So naturally, each hit is getting big. I mean, the effect of each hit is getting bigger.
But psi is not random.
Psi is not random. It's a gentle function and a very nice function. I mean, everything nice you can attribute to a function, you attribute to psi. So it is not random. It's a slowly varying function on the scale of scale of a. Well, yes, and xi. I mean, it is varying on the scale of xi. So, this is, let us say, the psi axis. Here is, so let us imagine there is a t up to here, and the function psi in this case looks like this. It starts from something and it is just growing like that. It is guiding the growth. Is the point clear? Psi is a smoothly increasing function, maybe decreasing, we do not know, some smoothly varying function. And the point is that if you take some reasonable variation of psi, let us say from here to here, from psi to delta psi, reasonable means not on the scale of A. That is unreasonably fast. So, then you will have many of these A's here. And you can assume that in this region, psi is not changing much. A is varying all over the place, but psi is not changing much. Psi, not psi, psi. Okay, yeah, unfortunately. This is not changing much. Yes. Yes. If what? T is large.
T is very large, then any continuous function, because any continuous function you do not differentiable, because
True. I mean, we did not even assume smooth and, in the sense of differentiable. Is that what you are saying? Yeah, need not. Yeah, correct. But you know, I mean, the ones we will deal with are like very smooth. Now, in this region, psi is not changing much. Therefore, you know, it's just like having, instead of A, you have psi times A. So, you can figure out the distribution here.
no, what I'm saying is that if T is very large, then anyway this will happen, because whatever the variation of A's are, if T is very large with respect to that, it is small. So this condition will anyway hold if T is very large.
Which condition?
That it is not very much in the.
No, it has nothing to do with T. It depends on the function psi. I mean, you know, you can imagine some function psi varying quite a lot. I mean, but there,
That's what I'm saying. If it is random, then it is.
no, okay, you can imagine non-random functions which vary a lot. I mean, but we are not including those. We are including smooth functions. I mean, maybe a good exercise to see how much can you relax this. But we are not worried because we are going to deal with explicit functions. Now, so the point is that therefore, in any window delta psi, psi will not vary much, A will vary a lot, and we are quite expert by now in finding the distribution, the probability distribution of what do you call it, the sums of these things. By that, okay, why do you need a sum? Because you have a something like a sum here, d psi, a psi, except it's modulated by some function. That is why we are motivated to do this. But if we are going to integrate over t, then you have to add this up and that up and that. So, it is back to the question somebody had asked, and which I think I have answered. What does the central limit theorem hold if you do not have identical variables, if they are varying? If the distribution is varying, does the central limit theorem hold for the sum? The answer is yes. All you have to do is to add up the variances. So, that is actually what we will do. I am just describing in words the calculation. Now, we will do the calculation. So, this is a sub calculation to derive the lemma, and then we will keep using the lemma once, twice, etc., and then we will get all the answers. So, the proof of the lemma, and you can divide it up if you want into some number of steps which is finite, which is 4, and we will just go over all 4 steps. Let B of delta t. So, we imagine we have broken everything up into, okay, so let me use blue. The whole time interval from 0 to t is broken up into many delta t's. Okay. choose any one of them, and let's just ask for B of delta t, which is defined as the integral 0 to delta t A of psi d psi. Okay. No hint of a gentle function here. This answer is going to be same for all the intervals, and the answer is something we know, we've worked out again and again and again, and so I'll write the answer. It's a Gaussian. So here it is. Okay, so we've defined this. Then now Chandrasekhar uses, and so in this lecture I will use the letter W rather than capital P for the probability distribution. So please bear with me with the change of notation. Capital W is the probability distribution. So if I ask for the probability distribution of B, which is of course characterized by delta t, then that is a Gaussian. It's equal to E. So it's the sum of random variables. Central limit is applying here, continuum case, and we are getting e to the minus b squared over 4q delta t divided by 4 pi q delta t to the power 3 by 2. 3 by 2 because we are in 3 dimensions, we have vector variables, we have one square root for each dimension. 3 square roots give you 3 by 2. Okay, so this is, as I told you, we are going to go in 4 parts. This is part 1 over. Shall we label them A, B, C, D? Okay, that's what I have done here, A. But don't get confused with the B. Okay, we'll call them 1, 2, 3, 4. 1, 2. Part 2. Right. Okay, so this is okay, right? We're just going to put things together. It's good to write them in pieces. Right, R. We're thinking of, remember we had discussed the problem of random flights. So there are steps and then you reach some point. So R, okay, is equal to psi yeah, so the philosophy is to somehow do the integral over psi in each delta t. Okay, that is what we are trying to do. So what is R? R is psi. I think I should put a subscript. I don't know what I should do. Sum over j, psi j of delta t. It's the jth 1, 2, 3 up to j, psi j delta t, which is not varying much on the scale of delta t, multiplied by the integral ax I dx I. 0 to delta t, I mean not, well, j delta t, j times delta t to j plus 1 delta t. You understand what we are doing. This is an addition. I mean, we are just in fact evaluating something like that for an arbitrary function psi. So we are breaking up 0 to t into subintervals delta t. Subintervals are labeled by j and they are of length delta t. Okay, so this is just the random variable written again. Okay. So this of course is B.
So that is the reason why we are allowed to sum over that j, because over that delta t psi j doesn't change.
Exactly. That is the whole point. That's right. There's some discretization. Yeah. Right, exactly. This is why we did it. Very perfectly put. So that's equal to sum over j psi of psi sub j of delta t. Oh, I now understand what I had done here. I have written j delta t here, which is also correct. J delta t is that time. So I thought I had made a mistake. So I put psi sub, same thing. Okay, okay. Psi j delta t times b of delta t. B of delta t is this thing. Okay. Okay. So let's call this a sum over, just to remind ourselves of random flights, Rj. So now we are thinking on a slightly coarser time scale than continuous time, on the scale of delta t, and each delta t there is a displacement small r. Okay. So we know the probability distribution of R, obviously, and that is simply, so that is 0.3 probability distribution of R. What is R? R sub j is this, right? Is essentially e to the minus b squared, except we have to account for the fact that there is a psi multiplying. There is a constant psi, that is all. So this will not change much, there will be a psi which will come in, is e to the minus, so let me just get it right. Okay, let me write only the exponential because there is no room here, r squared divided by 4 psi j squared q delta t. Nothing has happened. I mean, it's just that q has become q times psi j squared because there is a psi multiplying the each acceleration. Is this okay? All right. So now we are in a position to just add them all up and define and obtain our giant answer for W of capital R. So W of capital R, don't get deceived, R is not a displacement. Huh? This is the lemma at work. So it's 1 over, okay, so now let me write the right normalizations and everything. So this is the answer for the distribution R. This is 1 over 4 pi q integral 0 to t d psi psi squared of psi. Oh gosh, I need much more place. Okay. Over 4 pi q integral 0 to t d psi psi squared or psi squared. Okay, this is the denominator multiplied by e raised to minus mod r squared divided by essentially the same denominator. Okay, so where are we? For q integral 0 to t psi of psi squared. Okay, there's one step, crucial step which I have not done, so I'll just fill in now, and that is if the probability of Rj is this Rj, we need to compound these Rj's as R1 plus R2 plus R3. Each one, so now we, so in order to go from R's to capital R, I have to add up all the R's. It's again application of central limit theorem. the variances this time are changing. They are changing because of the psi j squared. Okay, but what we are instructed to do by the central limit theorem is to add the variances. So, the sum of the variances, sum over j psi j squared times q is the sum over the variances. So, that goes over into an integral when I make delta t small. So, that is the integral you are seeing.
So there is a square root.
Square root, yes. Here? Yeah. Correct. That's right. This is the sigma square of that distribution. Thank you. Okay. So, these are the steps that go into the lemma. I think you follow at least broadly what is going on. The main strategy is to split up into these subintervals of size delta t, where the general function doesn't vary much. Therefore, you can do your usual easy central limit theorem there with the variance psi times q, psi squared times q, and then you add up everything. I'm sure I could have presented it more compactly, but okay. All right. What is important for us for the rest of the development is just this lemma. So, if you are willing to say that you know, you are willing to believe the lemma, then you are okay, but it is better to understand the proof. The proof is not hard, it is just couched in some language which you have to unscramble. Are we ready to apply the lemma to this function? To apply the lemma, what we have to do is to put it in this form, but it is already basically of this form. All we need to do is identify what is psi. So, if you do not mind, we will go from here to here. Okay. Right. So, what is psi? Okay, so here we are, identify the function psi. Yes, somebody said something, e to the was correct. What was it? Also, don't forget this. I mean, it's there for the right. Okay. So, fine. So, it's e to the beta psi minus t. That we've done. What enters the answer? Well, the first thing is we have to square psi. Second, we have to integrate it. Both steps are easy. So, we can square this, we get a 2, we can integrate it, we get some answer. I will write the answer. So, then we check, please check 0 to t, do this please. G psi, psi squared, this is what we need in the lemma, is equal to 1 minus e to the minus 2 beta t divided by 2 beta. Therefore, we conclude we do know, answer here is yes. We can find the probability distribution, and here it is. So, I will write it all over again with a lot of commonalities, but does not matter. You, given that you started with u naught at time 0, maybe this bar is not a good notation. Okay, semicolon let us put. At time 0, t equal to 0, maybe put a bar, it is clearer. You started with velocity u naught. What is the probability that after time t the velocity is u? The answer is 1 over 2 pi q beta, 2 pi q over beta, 1 minus e to the minus 2 beta t raised to the power 3 by 2 e raised to minus u naught minus, oh no, multiplied by e to the minus beta t over 2q over beta 1 minus e to the minus 2 beta t. Okay, so let us just pause. Squared. Is it a Gaussian? At any given value of t, is it a Gaussian? It's a shifted Gaussian. I mean, why all this hesitation? Is it a Gaussian? Yes, okay. Here it is, okay. It's shifted. So there's an Newton here, and there's also something here. Just mathematically, where did this come from? This came from that integral over psi squared here. This one. Where did this come from? This came from the initial. Okay. But both of them goes to 0 as t goes to infinity. So for t much bigger than 1 over beta, you can drop that, and you can drop that, and you can drop that. So you recover W goes as 1 over 2 pi q beta, 2 pi q over beta to the 3 by 2 e to the minus u squared over 2q over beta. Is it of the Maxwell form? It is, provided we identify those coefficients with something to do with temperature and mass, because we have to match this with minus e to the minus half mu squared over kt. So that correspondence immediately gives us that q by beta is kt by m. So matching to Maxwell. Maxwell. Is this okay? Temperature, presumably you are working at a certain temperature, maybe room temperature. Mass is the mass of the colloidal particle. The radius of a colloidal particle is about a micron. So depending on the density, you can work out the. By the way, this question about gravity, you can sort of compensate for the effect of gravity by taking the mass or the density of the colloidal particle to be close to that of water. Experimentally very important, because otherwise you do everything and everything falls to the bottom. Experiment over. So you don't. So now, historical point. Who is the first person who studied carefully properties including fluctuations of colloidal particles? Time up? No. Okay. Not for me. No. Okay. Sorry. Okay. Half an hour only though. Okay. We'll do it. So his name was a French person. Shamik? Okay. Jean? Perrin. Okay. Yeah, no, we turn to him. Right. What was his nationality? French. Okay. Did he win the Nobel Prize? Yes. What did he win it for? Essentially this work, which allowed him to determine, something that was not known till then, Avogadro's number. You all think that Avogadro came and said, "This is my number." Does anybody know Avogadro's number? And I want to see if something happens. What is Avogadro's number? You know?
The number of particles in 1 mole.
1 gram mole. No, that is right, but what is the value? 23. Correct. It's a remarkable fact that all students remember 3 decimal places in Avogadro's number. They will not remember 3 decimal places for the speed of light, or anything else, but I don't know. It happens. Maybe there's a resonance between the 2 23s. I don't know. Anyway, let us not get into frivolity. Okay. So, and we are not actually worried about anything right now, other than, what is this equation telling us? Let's say in this day and age we know K, KT, M, we know everything. This Q and beta, what were they? Beta, by the way, please be warned, is not 1 over KT in my development. Beta is what appeared here. It's the friction term. It's related to 6 pi eta A. Therefore, okay, this is there, but what it is telling you is that this Q, where is it, is not independent of beta. In your model, you might have done it and gotten some answer, but that would have corresponded to a certain temperature. So, Q is the amplitude, or square root of Q is the amplitude of the accelerations that are coming in. They depend on the temperature, it turns out, and this is the way they depend. Okay, Q is like sigma squared. Is the point clear? So, this is rather, suddenly the physics comes in there. So, this is an important relation. It's important in various senses. First of all, it fixes Q. Q has something to do with all these fluctuations. Beta is a viscosity. When something goes against some friction, work is done and lost. So, energy is dissipated. So, beta has to do with dissipation. And there is an intimate relation, which is here is showing up, between fluctuations and dissipation. And there are things, results which go under the name of fluctuation dissipation theorems, and this is an illustration of one of them. It's a more general thing than just Brownian motion. Oh, by the way, I forgot to tell you, this is called Brownian motion, this motion. I'm sort of not going in order. Brownian motion. And of course, as usual, there's a history to everything. And who do you think this motion is named after? Brown, botanist, and everybody knows the story. But is he the first to observe it? Probably not. Who is the first to observe it? We don't know for sure, but it is somebody called Ingenhousz. Ingenhousz was a doctor, and he was a good doctor, or at least a famous doctor, in the sense that he was a doctor to the Emperor, Empress of Austria. And Ingenhousz, I suppose, did various things, but one of the things he did is he took a test tube full of alcohol, okay, and he sprinkled some charcoal on it, fine particles of charcoal, and he saw the particles moving around, and he recorded it, and then that was it. Now, in today's day and age, we don't know whether the particles that he saw, probably with the naked eye, were moving because of Brownian motion, maybe not, or maybe some random evaporation of alcohol, something evaporates, something moves. So, but these were all moving around. Okay, so this you will find in the article by, does anybody remember Montrol and somebody? Montrol and Lebowitz, correct. Yeah, so you will find a very good account of the history of Brownian motion. So this is called Brownian motion, and as far as we are concerned, this is the way we describe it through this Langevin equation, which is this equation, which we have now solved. We have not completed solving. We have solved for something. We have solved for the distribution of velocity. But we would like to know how much the particle moves. So let us find it. I think I can rub out most things here. Yes.
Does he use this kind of change notation? I mean, Q somehow reminds one of like wave-based.
No, he uses Q.
And also not gamma, but
No, he uses beta. I've been very faithful to Chandrasekhar. Actually, I had also forgotten because I had some old note. And this morning I checked, and it is that. Yes. Yeah, so don't get upset by changes of notation. It's good. But remember what it is. Don't put 1 over kt when you see this beta. Yeah, so symbols can have different meanings. One day in the TIFR interviews, somebody was asked something about what? Effect of gravity on photons or something. I mean, you all probably know that if a photon is shot upward, its wavelength increases because it does work against gravity. So there's probably a very, elegant general relativistic treatment of that. But in the rough and ready way, So then somebody asked him that, can you figure out what happens to the frequency? So he immediately wrote G H equals H nu, H cancels and go ahead. So be careful. Actually, I was in the interview committee. I was watching him. I couldn't see anything wrong, for a while. So then his various other deductions were quite wild. Okay. Notation, please be careful of notation. Good notation as yes.
So basically the temperature plays in a role. How often the particle gets the kick?
That's correct.
The temperature and the viscosity of the liquid. That's all.
How often the particle gets a kick? Often. Often we have not said how often it gets a kick, but the amplitude. Q, yeah. So what is the meaning of Q in terms of our parameters? It governs the amplitude of the noise, meaning the amount of force.
How hard the particle hits?
How hard? Yes. Correct. Yes. I couldn't hear. What is the average of? Oh, how would you generalize? You can put in a finite value. It's the simple idea of how you generalize a random walk to have a bias. So put in a bias. If you want to treat the effect of gravity, for instance, you could do that. That would be. But we are not. We are dealing with the simpler case here. Yes. It will lead to what? Deterministic. In that sense, it can be integrated and found, correct. Given that you know what happened to the noise.
Suddenly you are saying the probability distribution of U. So are you using the fact that the time distribution is same as the phase distribution?
No. I'm not using any fact of time distribution. I mean, just look at these pictures here. These are evolutions of even random walks. The question is it deterministic or not? Well, so if you knew a particular history of steps, that I took a left step, right step, it is deterministic. if you knew the history. Similarly here, when you integrate this differential equation, you have to integrate over A, which is a random variable. Now, if you know exactly how it varied, no problem, you get it. But the fact is, generally we don't know, sort of impossible to know. So therefore, we don't talk about a given bombardment, we talk about the distribution. So if you did this measurement again and again on the same colloidal particle, or if you did a whole host of other measurements, you would find the distribution. You can define what? Perfect. Right.
So if we freeze the time and if we talk about probability in a given time.
Yes.
So that probability will match the probability that we are talking in defined time.
Absolutely. Exactly. Just like, yes, yeah, go ahead.
We are actually assuming the, what can I say, the summing set code is ergoding, so we are measuring the space and time average is same actually.
No, space and time average is not the same as we emphasized in the beginning, but I mean, we are not assuming anything like that, we are just saying that this, unfortunately, we are reduced to the situation where we don't know exactly what the forces were, so we model them as random. Now, having modeled them as random in time, so having modeled them as random, it is clear from the definition of random that one history or one evolution will not give you the same answer as another. Therefore, if we want to make any statement at all after what happens after time t, it will not be about a given trajectory, because we will not be sure that we had that trajectory. The only statement we can make is of a distribution of the outcomes. So right now let me leave it at that, we will discuss further during t. Yes?
So the amplitude depends on P and beta and M. So basically, when you model a particle in a liquid, when modeling it by how hard the things hit. How hard the things hit depends on the temperature of the liquid, viscosity, and mass of the particle. So in the same liquid, if you have smaller mass, it hits.
No, but that is simply because we have chosen to model accelerations, not forces. I mean, the forces that are hitting will not be dependent on mass. I mean, Q characterizes random accelerations. M, okay, so that is just a parameter. But this is sort of traditional as defined by Chandrasekhar. So we have done that. Yes.
Yeah, so I just wanted to, in view of his question, I mean,
Yes.
some of the assumption is that the surrounding heat path is in a stationary state. The distribution is not changing.
Yes, yes, yes. Yeah, so we have a liquid with about 50 grams of liquid, and you only have one tiny colloidal particle, or maybe 100 of them. But
the viscosity will determine how hard it is getting hit. The molecules are hitting the colloidal particle, but it will determine the net
Acceleration.
the final effect.
Force of
The final effect of the distribution. I think only the temperature and mass.
you mean if you change? No, if,
Viscosity, so if the viscosity is very large, so then I think Q will also be large. Right?
you will follow beta, given a temperature and everything else.
Which means that your distribution is wider.
Yeah, that's right. Exactly.
That is a combined effect. That's a combined effect of the collision and the viscosity.
Right. So in a sense, we've written this down very, blithely, but both beta and the noise term, both are effects of molecular collisions, if you think about it. And how is it that you can separate out like this?
So somehow,
But we do.
so somehow it's like
Absolutely. Good, good. So there are two effects that happen. One is a bulk effect which you and I can see, something is falling, I mean perhaps. And the other one is too fast to see. It actually separates out like this. Beta. Beta is not the coefficient of viscosity, it is related to it. Beta has units inverse time. Okay, so let us see 6 pi eta a, I think beta is equal to 6 pi eta a. I am not sure, but we can figure out. But so you can relate, beta is related not only to the viscosity but the radius of the particle, but through some simple assumed Stokes relation. Okay, good. I hope we have 15 minutes left. Now I'll turn and look. Oh. Oh, okay. Never mind, we'll do it. Because you all have the lemma written down. The lemma is useful because it comes again and again and again. Somebody took my sheets. Oh. I would be dead. Right. Okay, so here we are. All right, now I'm going to give myself some room. Maybe I can't give myself so much room. Let me rub this up, doesn't matter. Okay, distribution of the displacement. Okay, I forgot. You should have put a heading there called distribution of velocity. Underline it with red. If you need to borrow a pen, I have a red pen. Distribution of, now write this and underline it again. As you see, I have underlined. When you write notes, it's useful to use colored pen because then you can easily pick out, you know, the parts, subparts, important results you can put in squares and so on. Use colored pens. Okay, well, how do we find a displacement? The answer is very easy. We integrate the velocity. Agreed? R0 we started with. This is R at time t, understood. So you integrate the velocity up to there. But we have found the velocity. Don't go to the step of distributions. We found it. Here is the equation for the solution by solving the differential equation that we had, and the answer is u0 e to the minus beta t. In other words, I am taking this to this side and adding there, plus tau, tau, tau. Thank you. Tau plus e to the minus beta tau, integral 0 to tau dxi e to the beta xi a of psi. I've just in toto taken that, except I've replaced t by tau. Now, so okay, well, so the first term we can integrate. You can integrate it in your head more or less. Integrate it and move it to the left hand side. R minus R0 minus U0 over beta 1 minus e to the minus beta t equals, let us just look at it, 0 to t d tau e to the minus beta tau multiplied by another function of tau, which happens to be an integral. Okay, big deal. 0 to tau dxi e to the beta xi axi. but this is in the form of an integral which is the product of two functions. Integral dx fx gx or f dg by dx. What do? Integrate by parts. You will all know how to integrate by parts. Only thing is you identify the functions well. So, okay, I mean, I hope I've done it right. So let me call this function df by d tau. You need two functions when you integrate by parts. So f is a function of it, and this one I'll call g. So integral d tau df by d tau g tau will be equal to fg evaluated with the proper limits minus the other integral, where you interchange the flips. So you know why we have done this, because the moment you take dg by d tau, it will be very easy. You can differentiate and find the. So we just do it. Let me just do it. It's a 1 minute answer. So this is e to the minus beta t by beta. That's the integral of f. So I'm trying to now write this as fg minus integral f dg by dt. Okay, keep that at the back of the mind. I mean, okay. And what is this integral? It's 0 to t. I mean, this is g. So I have to keep fg. This is g. So 0 to tau dxi e raised to beta xi axi. So far the fg has happened with a minus sign perhaps, and then some minus will become plus, and you will get 0 to t actually. There were two terms from 0 to t, but convince yourself that the tau equal to 0 will give you 0, because this function will be 0 when tau equals 0. Tau meaning t, sorry, t. I mean, it went from 0 to t, right? At this upper limit, you get this answer. At this lower limit, you get 0. And now you get the remaining term, which is f dg d tau. So let me just see. F. So the minus, and the signs you will be able to fix. Integral 0 to t. This came along, e to the minus beta t. Actually, it was e to the minus beta t over beta was the function. I took the beta out. And then I have to differentiate this. This is an integral. D by d tau of this is the function itself. So that's e to the beta tau. Why do I keep writing? Beta tau times a of tau. So these cancel. Okay. We can't very well simplify further, but it's all right. We'll live with what we have. But this is exactly in the form we need for our lemma, because this is integral d xi a of xi times gentle function of psi with proper identification of psi. One thing you have to do, of course, is this integral a tau d tau rewrite as a xi d xi. It's a dummy variable. and then group terms, and then you find that psi of psi is equal to, oh, I've exceeded time, okay, e raised to beta psi minus t divided by beta. Okay, so Shamik, I'm tempted to just write the final answer. Shall I just do it? Okay, sorry. Yeah. Okay, so now we are just going to say, use the lemma. With this psi, square it, integrate it, find it, and plug back. Having done that, you will find the answer for R. So let me just write the answer immediately. W of R and T, given that you started at R naught at t equal to 0, is equal to m beta squared over 2 pi kt 2 beta t minus 3 plus 4 e to the minus beta t plus e to the minus 2 beta t, close bracket, raised to the power minus 3 by 2 it should be. Okay. Okay, multiplied by e raised to essentially the same thing. I mean, not same thing of course, but okay, no, let's watch out. E raised to, you can write exp if you like. Okay, that's allowed. Minus, of course, this factor will come along, m beta squared and so on. 2 kt. So this is the, okay, so I have to copy all this again. 2 bt minus 3. I could have invented some shorthand, I did not. 4 e to the minus beta t plus e to the minus 2 beta t. But what multiplies m beta squared? It is the thing, the object that is normally distributed. It is not R because it depends on R naught. Nor is it R minus R naught because there is that other term. So it is that term, I mean once you account for it, it's all there. So R minus R naught, so it's R minus R naught minus U naught into 1 minus e to the minus beta t divided by beta, the whole squared. This is the answer. It's explicit, it's Gaussian, and it's all there. So you can ask again what happens if t becomes big. These terms will drop out. What happens to 3? 3 doesn't get small when t becomes big. It stays. But compared to this term, it becomes small. So you get something which ultimately becomes 1 over 4 pi dt to the 3 by 2 e raised to minus r naught and nothing else for dt. This is a form you have seen again and again, and we've recovered it again, where the diffusion constant d is equal to kt by m beta. Okay, I'll stop at this very moment. Very sorry, 7 minutes. Okay.